We will learn chapter 11, which is on rotational vectors and angular momentum. In this chapter, we will learn angular momentum, which is very similar to, which has relation to torque. The temporal period is, we learned this for, uniform circular motion, how long it takes for one circular repeated motion. And frequency is 1 over t, how many cycles per unit time. And we introduce here angular frequency, which is angular velocity, omega. How many rotations per unit time, omega. So omega is related to 2 pi over 2 pi over t for circular motion. 2 pi is one circular motion. To Newton's second law, we learned that the total force is net force is equal to momentum change rate of change in momentum, dp dt. Similar way, we can define angular momentum, which is related to time derivative of angular momentum is equal to torque. Same Newton's second law, but we introduce new angular quantity here called angular momentum. Here, tau is this. What should be the form of angular momentum? The angular momentum should have this form. You can actually prove this. You can prove this. The dl dt is, and this is 0 because p momentum is parallel to velocity. So r cross f is torque. So now tau, in the previous chapter we learned this. This is definition of torque, and this is I alpha. And now in this chapter we learn this. And L is to have this relation. Tau is equal to dl dt. L should be r cross p. R is vector, same vector as this one. Rotational axis to that force or the mass element or force acting position particle. So if this is the particle and this is axis of rotation, this particle is moving in a circular path. The angular momentum of this particle is r cross p. R is from the axis of rotation to the particle, and this linear momentum is mv, and angle between r and v is always 90 degrees. So angular momentum is pointing r cross p, pointing upward, z direction, pointing to z direction, and the magnitude of angular momentum is mvr. Okay? For most of the objects you will treat in this chapter, you can see here mr square is I, right, for a single particle. So this is here, L is mr squared times v over r. So in most cases, for sufficiently symmetric objects, we can say we can use this relation. L is equal to I omega. In most cases, you will treat in this chapter, you can apply this. So we found this throughout this chapter. We will keep using this simple relation. This is the most important part in this chapter. Tau is dt dl dt, and L is I omega or r cross f. This is all you will learn in this chapter. When tau is 0, external tau is 0, L should be constant with time. When total force is 0, linear momentum is constant with time. Linear momentum conservation. This is angular momentum conservation. If external torque is 0, then angular momentum is conserved. It's constant with time. This conservation of angular momentum, very, very important. One of the most important part in mechanics, okay? Up to midterm. If net force is 0, then angular momentum is conserved. That means L, which is I omega, is constant with time. So, for example, this skater rotates, okay? And while this skater rotates, while arms and legs far from the rotational axis, rotational inertia is large. And I omega is constant, and I omega is constant. And while she rotates, she can move her arm like this, close to her body, right? And also foot close to her body, so that mass distribution now is close to the rotational axis than previous. In this case, here mass distribution is closer to the axis of rotation, then I will decrease, right? I is r squared dm. R squared decrease, so I rotational inertia will decrease by doing this motion. And I omega, because external torque is 0, there's no torque acting on her to make angular, so I omega is constant. Then I decrease as during this motion, so omega should increase. Okay, so changes in rotational inertia should cause changes in angular speed because of this angular momentum conservation. Okay, once you understand this concept, it's not difficult to understand. Okay, precession is one of the most important parts in this chapter. You need to understand how precession works. This is one of the most difficult part in this chapter, difficult to understand, and also most important part in this chapter. It's very close, very similar to circular motion. If you understand why, moon satellite doesn't fall, even if there's a falling force, pulling force between Earth and satellite, the satellite doesn't fall, right? If you understand why, then you can understand this precession. Precession motion is related to why the rotating top doesn't fall. While you ride bicycle, why it doesn't fall? If you don't, ride the bicycle, if the wheel doesn't rotate, it easily fall down, right? But while you rotate this wheel, or while this top thingy is rotating, it doesn't fall, right? Why? The physical mechanism is very similar to the reason why, even if the Earth pulling down this satellite or moon, it doesn't fall down. Okay? Why? Why does the object can rotate, go through this circular motion without falling? Because this pulling force, attracting force, just uses what it does is it changes the momentum, right? It keeps changing the momentum direction, right? But the magnitude of the momentum doesn't change. If the magnitude of the momentum changes, that means it can just fall, right? So this is the pulling force, gravitational force here, which is centripetal force, and it's always perpendicular to the velocity, okay? So what this force does, it keeps changing the direction of the momentum, not the magnitude. That's why this object can keep rotating without falling, okay? Precession is the same thing. When this wheel is rotating this way, right, it has angular momentum, right? If some object is rotating, then angular momentum exists. So what is the direction of angular momentum in this way? This direction, which is parallel to omega, along the axis outward. Then if any force acts on this object, rotating object, for example, like mg, then what happens is torque acts on this object, right? Torque is r cross f. So torque direction is this direction. Angular momentum is outward, radially outward. What this torque can do is it can keep changing this direction of angular momentum. Force changes keeps changing direction of linear momentum so that the particle can go through this uniform circular motion. Here, this rotating body has angular momentum, and this torque, due to gravitational force, can keep changing this angular momentum direction. So that if angular momentum direction changes, what happens? This axis direction will change. So it goes through this rotational motion. This is precession. Okay? In both cases, the object do not fall down even with gravitational force. This object rotates this direction, and this mass goes circular path, goes through the circular. Very similar physical reason. This is precession. So it doesn't fall, even if there's a gravitational force, it doesn't fall down, but instead it goes through some rotational motion. The angular momentum keeps changing. Okay, so here, this is rotating, for example, this direction, counterclockwise. So angular momentum is in this direction, and there's gravitational force downward, but then torque is into the page. R cross F is into the page here, pointing into the page. what that does is it keeps changing this angular momentum direction. Instead of this make this top fall down, it keeps changing the angular momentum direction around this rotational loop. Okay, this is precession. This is why this top doesn't fall while it's rotating. If it stops rotating, it'll fall down. Right? Why a moving bicycle doesn't fall? Similar reason. Right? For example, if this person leans this way, okay, a little bit this way, if this wheel doesn't rotate, then he should just fall down due to gravitational force, right? There's a gravitational force downward, so he should just fall down into that direction. But if this wheel rotates, and if angular momentum is this way, what happens is from this wheel to this person, there's this R cross F, so angular momentum is going into the page. Torque is going into the page. This torque makes this person with this rotating body, the whole system, having angular momentum this way. This torque makes this angular momentum rotates through this way. So he can turn, actually, by leaning leftward, he can turn left instead of falling down. Okay? Because it should do this circular motion, change the direction of angular momentum. To gravitational force act to change, basically torque due to gravitational force act to change this angular momentum direction. Here's the end of chapter 11.